So good afternoon, everyone. My name is Behnam Khadam, and firstly, I would like to thank you for honoring me by this title and giving me the opportunity to present my work today. Today, I present my PhD work, which is a design, scale-up, and optimization of double emulsion processes, and supervised by Dr. Nida Othman. During the presentation, you will see the objectives and background of the work, and you will see the result of double emulsion preparation and the result of storage of double emulsion. And at the end, we will have final results, conclusions, and perspectives. The objective of this work has been studying theoretically and experimentally the preparation and storage of double emulsions in order to evaluate and determine the size of inner and outer droplets, and also the encapsulation efficiency of the system, which are the key parameters in order to control the quality of the final product. The application of double emulsions can be in many industries, but the main applications are for foods, cosmetics, and pharmaceutical industries. For food, it is possible to prepare low-calorie foods and increase the shelf life of the flavor. For cosmetic industries and pharmaceutical industries, it is mainly to control the release of the active agent or bringing the aqueous spill for oily creams. During this work, we focused on preparation and studying the water in oil in water double emulsion. In order to prepare our double emulsion, we use the famous two-step method, where in the first step, the NaCl solution is mixed with the oil phase, where we have oil and hydrophobic surfactant. The mixing has been done under high shear. And after having the primary emulsion, we mix this primary emulsion with an external aqueous phase, which is water plus hydrophilic surfactant, under lower shear rate in order to have bigger size of outer droplets and also preserve the encapsulated substance, which was salt in our study. In order to prepare the double emulsion, we used ultrasound, ultrathorax, and also 1 liter stir tank. By doing so, we could move in different scales of study. For example, the emulsification time, the size of the droplets, scales of turbulence, and we could study all of them. We use video probe, nano-ZS, optical microscopy, and also master sizer in order to follow the size of the double emulsion, the inner and outer droplets, and also we use conductometer to track the release of salt to the external aqueous phase. In order to put such a complex system in a modeling perspective, the best approach is using a coupled population balance equation, where we can track the change in the size and number of inner and outer droplets simultaneously by knowing the phenomena of interest. The first phenomena that is happening in the system is the swelling of inner droplets that leads to the swelling of outer droplets. The inner droplets can also escape to the external aqueous phase, which leads to the decrease of the size of outer droplets. Also, if there is energy in the system, the outer droplets can break, and this breakage would lead to the leakage of the inner phase to the external aqueous phase. And finally, the inner droplets can coalesce to each other, and also outer droplets can coalesce to each other. Now, by knowing the system, we can go and study different scales and different possibilities. The first part During the first part, we prepared our double emulsion using ultra-thorax rotor-stator. By using that, we could study the inertial subrange. For this system, our coupled population balance equation would be simplified to coalescence of outer droplets and also the breakage of outer droplets. The breakage of outer droplets would lead to the leakage of inner phase. And by knowing this leakage, we could develop a model for the volumetric flow rate of inner droplets to the external phase due to the broken surface of the outer droplets. And by having this, we could find the release of our NaCl. Solving this system helped us to find the size of inner and outer droplets and also the encapsulation efficiency in the system. As an example here, I show you the change in the energy in the system during the second step of preparation. We changed the steering rate from 3,400 RPM to 6,800 RPM. By doing so, the energy increased, and increasing in the energy leads the increase in the breakage rate in the system. Increasing the breakage would decrease the size of the outer droplets, which is on the left figure. And this decrease would continue until the equilibrium between breakage and coalescence happens. But on the right figure, we can see the release of the salt. We can see that the release continue to increase, which indicates that the release is only due to the breakage of the outer droplets. In the second step, we decided to study the preparation in the viscous subrange. To do so, we prepared our double emulsion using ultrasound for both steps. In order to study the change in the size and release, we decided to use the mean diameter correlations. We started to use the available correlations, which was theoretically developed for simple emulsions. And we adopted this correlation for double emulsion by adopting the important properties like viscosity and also adding the necessary phenomena. And similar to the inertial subrange, we defined a leakage model, where in this case, we defined our leakage coefficient to be inversely proportional to the size of the outer droplets to be able to include the breakage. And by optimizing the system, we can find the fitting parameters. And here, I would like to show you the effect of a dispersed phase. On the left figure, you can see the change in the outer droplet size by increasing the outer phase fraction. As we can see, the size of the droplets are increasing by increasing the outer phase fraction. This is due to decreasing the breakage. By increasing the dispersed phase, we will have damping effect in our system, which is correctly introduced into the model. And also on the right figure, we can see the change in the encapsulation efficiency by changing the outer phase fraction. We can see that the encapsulation efficiency is increasing, which is due to less breakage into the system. Now I would like to start showing you the result about the storage. We prepared a dilute double emulsion and we stored them in order to follow the size and release during a storage time. We followed the size over the first week and we noticed that the size of inner and outer droplets are increasing. But the question was that, is there coalescence happening or there is a swelling inside the system? To study that, we prepared a comparable oil in water simple emulsion, and we followed the size of that system, and we noticed that the simple emulsion is increasing in the size due to coalescence very slightly. So it is not that much significant over 19 days, but our double emulsion increased importantly in the size, which is due to the swelling. We continued studying our system, and we noticed that after the first peak of the storage, the droplets start to decrease in the size. But this decrease in the size is much smaller than their initial sizes. So there was the possibility of breakage happening inside the system due to overswelling. In order to confirm this, we theoretically calculated the size of outer droplets if only the inner phase go out. And we noticed that the size of the outer droplets, the real measured ones, are smaller than the calculated one, which was an indication of breakage happening inside the system due to overswelling. After knowing the phenomena inside the system, now it was time to model the system. We used our general coupled population balance equation, which was introduced earlier. And we decided to model the system up to the onset of the overswelling phenomena. By doing so, the coupled population balance equation would be simplified to what is presented here, where we will have the swelling of inner and swelling of outer droplets. To model the swelling phenomena, we use the membrane permeability model, and we noticed that there is a need to correctly use the old membrane permeability model. And we introduced this correction inside the model by insisting in having the Laplace pressure in order to follow the size for submicronic inner droplets. We extended the model for the full distribution, and based on that, we also developed a model to follow the size of the outer droplets due to the swelling. And also, there will be escape in the system where the inner droplets will approach the external layer and will coalesce to the external aqueous space. For modeling the escape, we used the de-wetting model of Kang et al., which was developed for the single size droplets. We extended it for to the full distribution, and we also developed a model in order to follow the change in the size of outer droplets due to the escape of inner droplets. By solving this system, we can track the size of inner and outer droplets, and also to find the encapsulation efficiency. Here, I would like to show you the result, one of the results, which was changing the fraction of the salt, encapsulated salt in the system. And this figure, you can see the results right after preparation, which is the pink results. And you can see the other results on the right side, which indicates that the system is swelling for different amounts of salt fractions. And also you can see the validation of the system to the experimental results. The lines are indicating the modeling results. We will see the result of model for inner droplets in the next slide, but in general, by increasing the salt fraction, the inner droplet size swell, and the swelling of inner droplets increase, and also the swelling of outer droplets increase. And also by increasing the salt fraction, we notice that the release decreased until a negligible release for higher salt fractions. In this slide, I would like to discuss about the inner size of the droplets during the storage. One of the difficulty is that there is no direct method in order to find the size of inner droplets. On this figure, you can see the change in the size of inner droplets, a blue one as the swelling model and black one as NMR approach. So we used NMR to measure the inner the size of inner droplets, and we could validate the swelling model and also indicate that the inner droplet size can be measured by using the NMR method. As a summary, during the preparation step, we could see that by increasing the inner phase and outer phase, the encapsulation efficiency and outer droplet size increase. And by increasing the energy or emulsification time during the second step of preparation, the encapsulation efficiency and the outer droplet size decrease. Also, we found the indication that the leakage of inner phase strongly depends on the breakage of the outer droplets. During the storage, we found that the swelling results in the increase in the size of inner and outer droplets. And also, there is a overswelling that can happen into the system, which leads to the breakage of the outer droplets and finally the leakage of inner phase. And we noticed that by increasing the salt fraction, we can have the change in the swelling increases and the escape decreases in the system. And we also noticed, which is mainly this result is available inside the manuscript, that the Laplace pressure needs to be in the swelling model, especially for the submicronic size inner droplets in order to accurately predict the sizes. And finally, we established the method to find the size of inner droplets based on the NMR method and also validate our swelling model. As a general conclusion and result, we can say that the coupled population balance models are a good tool to accurately predict the size of inner and outer droplets and also the encapsulation efficiency or release inside the system. The main contributions that we had in this work was introducing the coupled population balance equation and also proposing two leakage models, one for population balance model and one for the coupling with correlation of mean diameter of outer droplets. And we provided the swelling model for the outer DST based on the swelling of inner droplets, and also we introduced the correct use of the swelling model for submicron inner droplets, and also we developed a model to follow the change in the outer droplets due to the escape of inner droplets, and also we introduced the correct use of outer droplet properties. All the works that was presented here, each part was published in different articles, and they are available here. And as perspectives, for sure there are many perspectives, many other topics to be followed after this work. But the main ones that I can name is using the PBM for the dissipative sub-range, and also to develop some models for the rheological properties of outer droplets based on the inner, based on the effect of inner droplets, some properties like viscosity. And it would be very interesting to develop a breakage kernel for the overswelling breakdown and to be able to find the final droplet size also after that phenomena. And also a model for the dependency of the permeability coefficient on time over the initial stage of swelling phenomena would be very interesting. This work was funded by Marie Curie, grant agreement number 675251. It was done in University of Lyon, Legib laboratory. It was part of the ModLife network, and our industrial collaborator was Unilever. Thank you for your attention, and I would be happy to answer your questions.
Thank you very much.
So thank you, Mr. Ben Kadem. Very, very nice work. As a matter of fact, I myself work on double emission processes to produce dry emulsion for food application. It was what we called dry emulsion, dry vinaigrette. Mm-hmm. Not sure that, as far as I know, I'm not sure that this dry vinaigrette reached the targeted market, but it was a very nice research too. And I think that's a very nice field of research with both contribution of chemical engineering and formulation chemistry, formulation processes, I would say. And I think it's a very nice cooperation between this formulation chemistry and the processes. And so I've been told that today you've been hired by Anchor in Germany.
Yes.
And so I'm sure you will have an outstanding career in chemical engineering from your PhD. And I want to congratulate you for this very nice R&D work.
Thank you, Francois. Yes, for sure, I would like to also go and study the work that you described. It would be very interesting for me. And yes, now I'm working at Henkel as the R&D manager for the digital transformation topics, and mainly for predictive analytics and bringing digital and IoT tools for the beauty care to the market.
Beauty care, cosmetics. Okay. And for the dry emulsion, after this double emulsion, we have to spray dry this emulsion, and so that it kept very steady, very stable.
Interesting. I will for sure have a good look at your works, and maybe I will come back to you for some questions.
Or I think it was 20 years ago.
Oh, wow.
For a chemical company.
Oh, wow.
So I was in advance compared to your PhD, maybe. Just joking.
Oh, wow.
Well, so Mr. Benham Kadem, now in the name of SFGP.
Just a second. Can you stop sharing your slide? I would like to share one slide.
Sure, sure.
Thanks you.
Okay.
Just a second.
Yeah, thank you, Jean-François.
Okay.
So, Mr. Benham Kadem, in the name of SFGP, I'm very happy to award you this 2019 SFGP PhD prize. And I sincerely want to congratulate you for your outstanding research works.
Thank you so much. It's a great honor for me, and I'm so happy to be part of the association and receive this title. And I don't know how to express my happiness, but it gave me great pleasure. And I thank you all for choosing me and giving me this opportunity.
You're welcome. But and now